I really appreciate everyone being here today. It looks like we have a great group of participants, and as Meredith mentioned, we have a fairly full agenda, so I won't spend too much time on the opening here. But I did want to just mention to this community in particular, very quickly, that some of you are aware the International Conference on Arctic Research Planning is a decadal activity that's undertaken under the umbrella of IASC, and the next one of these planning conferences will take place in 2025 in Boulder, and the IASC is currently in the process of developing the framework for ICARP, and as part of that, they're actively seeking contributors to what are known as research priority teams, RPTs. And so I want to make sure that the U.S. Arctic atmospheric science community is aware of this process and is aware of the fact that you can nominate yourself or others within our community to serve on these research priority teams. It is quite important that we have representation from atmospheric scientists on these teams. And of course, this community in particular might have people that can contribute to that. So I'm going to drop in the chat a link to the RPTs in general. And if you think you or someone you know might be interested in serving on one of these teams, please do submit a nomination. The nominations are due at the end of this month, so I recognize the timeline is quite short. But I just wanted to make sure that that was broadcast within this community. So I will drop that link in the chat right now. And then from there, we will kick off our meeting. This month's meeting is focused on the HiLAT project, which is a DOE-led effort to advance and leverage our modeling capabilities at high latitudes. And so we have several participants or contributors to that team here today. We have Wilbert Weijer, who is leading the HiLAT effort. And then we have from the University of Colorado, John Cassano, Mark Seefeldt, as well as Hailong Wang from Pacific Northwest National Laboratory. And I don't have the order of speakers in front of me. I apologize, but Wilbert, I don't know if you want to give just a very quick introduction and then kick off the presentations from there. Does that work?
Sure, that sounds good.
Great, thank you.
My slides. Yeah, so I'll give a very brief introduction to the HiLAT-RASM project. I'm co-leading, I'm lead PI at HiLAT-RASM, co-leading with Hailong and Wisław, and this is, of course, on behalf of the entire team. So HiLAT application and testing of Earth system models is a science-focused area that is funded by Department of Energy's Regional and Global Model Analysis Program area. The primary partners in HiLAT are Los Alamos National Laboratory and Pacific Northwest National Laboratory. We've been collaborating on this since 2015, and currently we're in our third phase. The Regional Arctic System Model project is funded by DOE, ONR, NSF, and other funding sources. It has been in existence since 2007. And the primary project partners there are Naval Postgraduate School, and Wisław is the lead PI of HiLAT-RASM, of the RASM project, and the University of Colorado Boulder and the University of Washington. And of course, we have John and Mark representing CEO Boulder here. So HiLAT-RASM have officially been collaborating since 2019, and we call ourselves the HiLAT-RASM project. And we have also several other collaborators, Penn State, Indiana University, University of Alaska, and another collaborator at the University of Washington. Just as a brief introduction to what we are focusing on, so the Arctic Earth system's response to external forcing depends critically on many feedbacks, and many of them are here represented in this figure by Han et al. And these feedbacks are chains of processes that amplify or attenuate Arctic warming. Many feedbacks are very well known, they have been well studied, but still they often remain quite poorly represented by Earth system models, for instance, the ice-albedo feedback. Other complex feedbacks are poorly understood or quantified, so they are poorly constrained by observations, poorly represented by Earth system models, and often they involve interactions between several Earth system components. And those are the feedbacks that we, as the interdisciplinary HiLAT-RASM project, are really focusing on. So the goal of the project is to understand, quantify, and compare, and whenever feasible, to improve the model representation of multi-component feedbacks on Arctic amplification. We want to do that by developing what we call a unifying framework to analyze feedbacks across Earth system components using a hierarchy of modeling approaches. We organized our science in 3 science areas that are very complementary and overlapping in many ways. So science area 1 focuses on the role of meridional heat and moisture transports in Arctic amplification. Science area 2 focuses on more regional perspectives, the atmosphere, ice, ocean interactions in the Arctic. And science area 3 focuses on the role of biophysical land-sea interactions on Arctic amplification. We kind of have the cross-cutting capability areas that help us execute our research. So these are indicated here by the concentric rings in this diagram. So on the one hand, we want to address our problems by looking at, like CMIP, existing data sets, reanalysis data, observations, and use metrics, well-chosen metrics to diagnose the processes that we're interested in. So this is capability area 1. Capability area 2 will also be performing targeted experimentation with our state-of-the-science models HiLAT-RASM, Arctic, and RASM. And a very novel approach will be using machine learning assisted reduced auto modeling to address our problems. So these are the 3 capability areas that we bring to bear to the 3 science areas. We have a HiLAT-RASM project has a strong overlap with priority area 2 in particular of IARPC, priority area on Arctic systems interactions. Objective 2.1 in particular, to advance understanding of Arctic amplification and the associated connections with lower latitudes. 2.1.1, 2.1.3, 5, 6, and 7 all are very relevant for HiLAT-RASM objectives. Of course, we also are strongly aligned with monitoring, observing, modeling, and prediction foundational activity, in particular contributing to MOMP1 to coordinate activities and communities of practice that bring together Arctic modeling, observing, monitoring, and prediction to advance Arctic research. We are involved in several model intercomparison activities, in particular polar cordex, that John will talk about. And MOM2 to support assessment gaps analysis, and intercomparisons to understand observational and modeling needs in Arctic research. So this is a very, very high level, a very quick introduction to the HiLAT-RASM project. And of course, everybody here on this team on this call is interested to hear more from Mark. He will talk about HiLAT-RASM modeling tools, HiLAT-RASM, Arctic, and RASM. From John, who will be talking about atmospheric rivers, as well as the Arctic Cortex mosaic boundary layer model intercomparison project. And finally, Hailong, who will be talking about the activities ongoing at Pacific Northwest National Lab on Arctic amplification, focusing on local feedbacks and connections with lower latitudes. So with that, I'll hand it over to Mark.
All right, thank you, Wilbert. So, welcome everybody. Thank you for attending this presentation. I'm here to talk about the modeling tools that we use with the HiLAT-RASM project, specifically HiLAT-RASM Arctic and RASM, the Regional Arctic System Model. And in Wilbert's diagram, this is part of the CA2 capability area. The objective that we're looking at with these models is to apply physically based numerical modeling tools with a focus on simulating the relevant processes of the Arctic climate system. The flagship for this effort is the Energy Exascale Earth System Model, or ESM, which is a global Earth system model with a regionally refined resolution in the Arctic and subarctic, which we're calling HiLAT-RASM Arctic. The E3SM Arctic is critical for proposed studies of feedbacks on the Arctic amplification, specifically those related to the interactions with the larger global climate system. We have the Regional Arctic System Model, or RASM, which is a regional Earth system model with a focus on the Arctic Ocean, hydrosphere, hydrology, and biogeochemistry. And RASM is then has a focus for regional feedbacks. So looking at a graphic that we have for the Arctic amplification and what we're studying with the HiLAT-RASM project, we can see that the E3SM Arctic is a freely evolving global ESM that captures the interactions with the Arctic and the rest of the globe. And it can be run with various greenhouse gas forcing, slab ocean, cloud blocking configurations. RASM, on the other hand, is a downscaled regional Earth system model, which uses Arctic-specific physics. We're also able to more easily constrain RASM to isolate feedbacks in our investigations of Arctic amplification. It also has the capability to reach very high resolutions, 2 kilometers in the ocean, at less computational cost than we would have with the global E3SM Arctic. Both of these models focus on the Arctic climate system, and both of them operate in fully coupled and data-first configurations, and both of them can run BTC simulations. The E3SM, for those that are less familiar with it, is a coupled Earth system model with independent components for land, ocean, sea ice, land surface, and land ice, and includes a driver and coupler for exchange of fluxes on it. E3SM version 0 was initiated from a branch from CSM, and then version 1 introduced notable changes from CSM, including the EAM, the E3SM atmosphere model, MPAS size, MPAS ocean, ELM, which is the E3SM land model, and Mosaic. And E3SM version 2.1 is the current working version. So E3SM Arctic has a regionally refined model or mesh over the focus on the Arctic and the subarctic. Specifically, the ocean sea ice mesh is 30 to 60 kilometers in the southern hemisphere, 30 kilometers in the tropics, and then 10 kilometers in the Arctic and subarctic. A key emphasis with the ocean simulations for both E3SM Arctic and RASM is be able to fully resolve transport areas in the Arctic that play a large role in the Arctic climate system and are critical in solving energy budgets. So with that, we have the quick plot here for the ocean to emphasize the transport. We're looking at improved resolution of the ocean sea ice regional refined mesh has been found to be critical Arctic and subarctic exchanges. We're highlighting this in the right panel showing E3SM low resolution, and the left set of panels E3SM Arctic, and the fact that E3SM Arctic is able to much better resolve the Norwegian coastal current, and the stratification representation of these currents is key in representing fluxes of volume and fresh water into and out of the Arctic. The E3SM Arctic atmosphere land mesh is a resolution of 0.25 in the Panarctic and 1 degree elsewhere. So this is focusing on the storm activity in North Pacific, North Atlantic, and this is also developed with collaborations with Sandia National Lab and University of Alaska Fairbanks collaborators. The simulations that we've completed in year 1 of phase 3 are using E3SM version 2.1 Arctic branch. We have a fully coupled with regional refined mesh of ocean, ice, and atmosphere land with 1950 conditions. We have 2 simulations of this, 300 years, 200 years. Fully coupled regional mesh in the ocean, sea ice, low resolution atmosphere land, 300 years to 1950 conditions. And we also have a comparison one of the standard low res E3SM with 1950 conditions running for 600 years. And then the big simulation that we're getting into now with the atmospheric studies in particular, the fully coupled regional mesh for ocean, sea ice, atmosphere land with the historical greenhouse gases that we run from 1950 to 2014. Here's an animation showing the capabilities and the benefits of the E3SM Arctic. We have trajectories in the green, indicating the atmospheric function. And then we have the sea ice represented with the white. And on this cross section, we're also able to see ocean temperatures with it. And we also see plumes of moisture coming along with the interactions with cyclones, as well as atmospheric rivers going in it. And we're able to see with this animation just the interactions we're able to do with the Arctic climate system by having this high resolution, fully coupled model of the Arctic. This was completed with the Texas Advanced Computing Center with Francesco Samson graduating with them, and they worked with this simulation. Now, if we read the Arctic system model, this is a limited area coupled land ocean sea ice model focused on climate simulation directly. As was highlighted in the other opening, it's a collaborative project from University of Colorado in the atmosphere with the work model, land and stream flow with the University of Washington, and naval postgraduate flow with the ocean, sea ice, and upper column itself.
Mark, sorry to interrupt, but your audio seems to be degrading over time. And I don't know if you have a second mic that you could test, but this one, I'm starting to have trouble hearing you.
All right. Let's see.
Is it better now?
Much better. Yes, thank you.
All right, sorry about that. All right, so with RASM, we're looking at dynamical downscaling of reanalyses, error interim, error 5, CFS, as well as ESMs. We've done some simulations with the CSM decadal prediction large ensemble, as well as a trial simulation, including of downscaling at E3SM. We're able to optimize experiments with varying parameter space, can also be verified against observations in space and time. Our current default simulation is ocean sea ice at 9 kilometers, atmosphere land at 50 kilometers, covering the Arctic climate system. We're also able to do ocean sea ice simulations at 9 and 2 kilometers with the data atmosphere. And we have plans to go forward with that of looking at ocean sea ice at 2 kilometers, atmosphere land at 25 kilometers. With RASM, we're going to be replacing VIC with the Community Terrestrial System Model, CTSM, as the land model, as well as upgrading WRF to version 4.5. And also looking at running standalone WRF simulations with lower ocean and sea ice conditions provided by RASM ocean sea ice simulations to provide more extended capabilities, reduce computational costs. And that covers my introduction on the modeling projects.
Great. Thanks, Mark. I will share now. Okay, so I want to talk about some science activity that's going on that the group Mark and I have at University of Colorado are working on. And collaborating with other partners on HiLAT-RASM. So first I'm going to talk about, atmospheric rivers and their impacts on surface energy budget. And then I will also talk about some work we're doing with Arctic Cordex using mosaic observations to look at boundary layer intercomparison across models. So for the atmospheric river impacts on surface energy budget, we have a postdoc in our group, Chen Zhang, that is looking at this. And the question we're really interested in is quantifying what the impact of atmospheric rivers is on the surface energy budget in the Arctic. And Chen is leading a manuscript on that. We've identified atmospheric rivers using 85th percentile of integrated vapor transport in ERA 5. We then calculate surface flux anomalies during atmospheric river events, and then assess these impacts in a climatological context based on both the size of the anomaly, spatially varying across our study domain, as well as the AR frequency. And here's just one example of sort of the results that we get out of this. So the top panel is showing downwelling long wave radiation anomalies for 4 seasons. And then the bottom panel is showing the relative contribution of these anomalies to the overall surface energy budget as a percent. And so looking at that top figure, what you see is that the largest anomalies in excess of 50 watts per meter squared occur in the winter. Small anomalies over the Arctic Ocean in the summer. And then a consistently large impact is seen over Greenland. If we look at the relative contribution of long wave down anomalies relative to the mean surface energy budget, we see large percent impacts over the land. That's a reflection of the fact that the surface energy budget, the net surface energy budget is pretty small over the land. But what really stands out over the Arctic Ocean is that the largest relative contribution, about 20 to 30%, occurs over in the spring over the sea ice, suggesting the importance of atmospheric rivers for sea ice melt and onset. And then here are just the total surface energy budget anomalies associated with atmospheric rivers in the top, and this is the percent contribution. And so again, we see a large impact in winter over land, but also over the Arctic Ocean and near the ice edge. We see small impacts in the summer over the sea ice, intermediate over land, and biggest over Greenland. And then the bottom figure is just showing the surface temperature anomalies. And of course, those correspond quite closely with the surface energy budget anomalies. So we're wrapping up this initial work that's based on reanalysis, but we expect to be doing additional work, look at coupled processes and their response to atmospheric rivers coming up in the near future using both E3SM and RASM simulations. And then to switch topics, I'm leading an effort in Arctic CORDEX. So CORDEX is a coordinated regional downscaling experiment. So this is just regional climate modeling groups from all over, here focused on the Arctic. We're going to be using observations collected during Mosaic, the year-long expedition from 2019 to 2020 in the Central Arctic, looking at the boundary layer. And so the aspects that we're going to be evaluating these Arctic CORDEX model simulations is their ability to simulate the variety of boundary layer stability profiles that were observed on Mosaic, and then how well they simulate the different frequency of these stability regimes, and then finally looking at their ability to simulate radiative and mechanical forcing associated with the different stability regimes. And then the bottom half of the slide just lists the different modeling groups that are involved. And you'll see at the top left, CU, my group, and group at NOAA. It's contributing WRF, RASM, and CAFS, the coupled Arctic forecast system. And then DOE, PNNL, Hailong's group is going to be providing output from E3SM for this evaluation. So just a couple of quick slides about what this evaluation looks like. So we're using data analysis technique known as self-organizing maps that allowed us to analyze the about 1,400 radiosonde profiles collected during the year-long Mosaic expedition and classify them into this range of potential temperature profiles that are shown here. So each of these panels is showing height from the surface to 1,000 meters. And then the bottom axis is temperature anomaly relative to that at 1,000 meters above ground from 0 to minus 20 Kelvin. And so this is just showing us all the different types of stability profiles. And you see, what you would sort of expect, so top right are these very strongly stable profiles, but on the left side, you see cases with different depth, near neutral, almost well-mixed conditions capped by varying strength inversions. And that's all, and the black lines are based on the observations. And then there are 3 colored lines on here showing 3 different forecast durations, 1, 2, and 3 days from the CAF system. And what really impressed us when we did this analysis to begin with is the ability of CAFs to represent quite accurately the full range of stability profiles that was observed. But those results were basically taking the observations in the model forecasts and just putting them into those different stability profiles on their own, neglecting what when they were being forecast. So our next part in this project is to look at how frequently the different stability regimes are observed and then how frequently the models simulate them. So here the different colored bars are showing the different stability regimes. The pink is the strong stability, the brown at the bottom is near neutral, and these are arranged in increasing stability from left to right in the top panel, and the top panel is showing how frequently annually on the left, and then in the 4 seasons, each of these different stability regimes is observed in the mosaic observations. The bottom panel shows the difference in frequency of what CAFS is simulating compared to what was observed. And we see CAFS is struggling with some of these stability regimes, under simulating them. These are ones that have weaker stability near the surface, but strong stability aloft. And then the final thing that we're doing is looking at radiative and mechanical forcing that drives stability in the atmosphere. And right now we're looking at downwelling long wave radiation, which is a plot on the left, and then 10-meter wind speed to represent near surface wind shear and mechanical generation of turbulence on the right. And then what we've done for each of the different stability regimes, again, arranged from strong stability on the left to weak stability on the right, is create a box plot of the radiation and wind speed observed for each of the stability regimes in the model and in the observations. And then the 0 line here is showing if there were no difference between the model and the observations, and then if the bars are above, it indicates the model has larger values, and if it's below, the models have smaller values. And so we can see CAFS is, when it's simulating these different stability regimes, it's generally doing so with a bit more downwelling long wave radiation than what is observed. And then the winds tend to be pretty accurate, close to what's observed for the strong stability, but with increasing positive wind speed biases as we move to the weaker stability regimes. So I think I will end with that, and we won't take questions now, but we'll turn over to Hailong now.
Right. You see my full screen?
Yes.
Okay, cool. Yeah, thank you all. So yeah, again, my name is Hailong Wang. I'm an earth scientist at the Pacific Northwest National Lab. I'm going to present some work contributed by many HiLAT-RASM team members and our collaborators. So this schematic shows the processes that we're studying for the Arctic amplification in the current phase 3 of the HiLAT-RASM project. This schematic highlights the highly interconnected nature of the Earth system components within the Arctic, such as the atmosphere, ice, ocean surface interactions and feedback processes, and the atmospheric and ocean oceanic transport between the Arctic and lower latitudes. So they're all relevant to the Arctic amplification. So this is the first year of our current project phase. So we're making progress at many fronts. Instead of going deep on one topic, I'm going to highlight some results on various tasks. I will start with our AA quantification metrics and feedback decomposition, and then highlight 3 papers on AA and atmosphere rivers, and finally provide more specifics about our participation in the mosaic intercomparison with E3SM and E3SM Arctic refined model. So Arctic amplification was originally defined to describe the phenomenon that on average, the Arctic has warmed faster than the global globe since the 1980s, as shown here. So this concept has also been used to describe a spatial temporal distribution of the amplified warming trends in the Arctic. For example, in this earlier study, we showed that the magnitude of AA is strongest in the cold season near 80° north, where the warming trends are almost over 6 times of the global mean. However, there are many different AA quantification metrics used in the literature. For example, we have a list of 7 metrics in this table. A1 is commonly used metric with difference in surface air temperature anomalies between the Arctic and the global mean, and A5 is a similar metric, involves the ratio of the 2 anomalies. These 2 metrics directly based on temperature anomalies tend to have large temporal variability due to the internal climate variability in the Arctic surface air temperature. Our metric A2 is defined as the ratio of the surface air temperature linear trends over the Arctic and the global average. Is particularly useful for assessing the Arctic change on multi-decadal and longer timescales. There are other metrics introduce appropriate weighting by scaling the Arctic temperature anomaly to the magnitude of variability in each region. So each of these metrics has its own advantages and considerations when studying AA. In this work led by my postdoc Yiling, one of the goals is to compare the established metrics for AA and assess their consistency during different time periods based on observation, reanalysis, and model simulated data sets. So as expected, the different AA metrics give very different magnitudes of the annual mean Arctic amplification in recent decades as you compare the different panels. Some of them have very large temporal variability. And then we also, if you also look at the seasonal variation here, annual in black and winter in DJF in blue and summer JJA in red, you can see that the seasonal most of the metrics show the winter time has much stronger AA than the summer. And we also see even greater variability in AA for winter time. So another goal of this study is to quantify contribution of individual feedbacks to the amplified Arctic warming. We first quantify the individual feedbacks using the traditional Kernel-Gregory regression method, and then apply them to a moist energy balance model by removing one feedback at a time. The difference in the Arctic warming is considered as the contribution from the specific feedback. So just for example here, our initial set of tests show that our albedo and lapse rate feedback contribute the strongest to the warming based during 1980 to 2022 based on the era 5. Here, just a demonstration of this tool. So in this study led by a graduate student with Chang Fu at the University of Washington, we found that the internal climate variability increased AA during 1980 to 2022. Here, AA is defined as the ratio of the surface air temperature linear trends between the Arctic and the global average. As shown in the figure, the observed AA is much stronger than any of the CMIP6 models. So he then trained a machine learning algorithm to identify the contribution of internal variability and external forcing to the surface warming, and found that the internal variability actually increased the Arctic warming but decreased global warming. After the contribution of internal variability is removed from the observational data set, then you will see that the remaining externally forced AA in observations shows much better agreement with the model ensemble mean here. So indicate that a better understanding of the decadal variability would help improve the AA predictability. So now we switch gears to Arctic atmosphere rivers. On top of the Arctic warming trends, Arctic moisture has been increasing too. Here, the figures show the increasing trend of total column water from era 5 in 4 seasons during 1981 to 2021. The strong seasonal and spatial variation. Interesting science questions would be how important is the forward moisture transport by ARs, and why is there such a strong spatial variability? So in this paper led by my postdoc, Wilbert Ma, we found that a strong contrast in the observed AR trends between the Pacific sector and the Atlantic sector, shown here. Both era 5 and era 2 show this contrast as indicated in the bottom panel. However, CMF6 models and CESM2 large ensemble, they couldn't capture the spatial difference, the contrast. But with the prescribed SST and CIs, then CESM2 can actually reproduce it, as shown in this purple box here in the bottom panel. So this points to the role of, again, to the internal variability. We looked at observed SST trend, which shows negative IPO and positive AMO patterns. So those two different decadal variabilities have different impacts through their moisture and dynamic effect on the different sectors of the Arctic. I'm not going into details, but those two can partly explain the difference between those two sectors. And in a relevant study, also led by Weimin, we characterized winter extreme warming events in the high Arctic. The composite of this event shows that both downward long wave radiation and the surface turbulent heat fluxes play comparable roles in driving those warming events, but downward long wave radiation is dominant over the higher latitude, and turbulent heat flux dominant over a lower latitude. We also found that most of those events actually occur under AR conditions. As you show that here in the figure, a dipole pattern in the sea level pressure anomalies with high anomaly located southeast and low anomaly located west of the event region, favoring the moisture and heat transport as the drivers of those events. And lastly, time's running out. I just want to introduce a bit more details about the mosaic model intercomparison from E3SM Arctic and the E3SM model. John has talked about the comparison also as part of the Arctic Codex activity. So we're also participating in this, led by Felix Pethan and Andrew Gettleman. They are focusing on the boundary layer and cloud processes, as well as sea ice and upper ocean response to the atmospheric forcing. So their initial comparison show that the model resolution really matters, because for the event-based short-term comparison, the mosaic, the model observation, the ship is only close to very few points if the resolution is too coarse. And also nudge scale circulation is also critical to look at the fast shift of temperature based on the events. So lastly, I'd like to highlight the preliminary analysis of the mosaic E3SM aerosol tagging simulation led by Ian Baxter, who is a PhD student with Tsinghua at UC Santa Barbara, who is currently visiting me as on a DOE fellowship. So aerosols, especially light-absorbing aerosols such as black carbon and dust, are important to clouds, surface albedo, and marine biogeochemical cycle in the Arctic. As part of this model intercomparison activity, we set up the E3SM model with aerosol source tag to study extreme aerosol transport to the Arctic, which is also known as aerosol atmospheric rivers. MERA-2 was able to capture such extreme event transport during the Mosaic campaign in April 2020, as shown here. So the initial HiLAT-RASM simulation was also conducted. Our initial test was conducted with SSP 245 emissions for 2019 to 2020. So in order to capture this kind of strong aerosol plume, like showing here, one event here, we need observed high frequency emissions, especially from wildfires. So we're currently processing the GFET fire emissions, and we'll do more new simulation and more analysis on this. So with that, I would just list the papers. Some of them are in review, and some of them are to be submitted. So I just list here. We'll have some time to answer questions. Thank you.
Excellent. Thank you, Hailong, and thank you, everybody, for those great presentations. I know that John and Mark have to leave fairly soon to get ready for a class. I don't know if any of the group have quick questions for John and Mark specifically, and if not, for the broader team here, for the HiLAT-RASM team. There's a lot of information provided and a lot of good activities actually also to be aware of. Yes, it looks like we have a hand. Andy, please go ahead.
Hi, sorry, I had joined late and maybe this question would have been answered, and it's really good to see everybody. When can you talk more, John or Mark or anyone, about CAFs and when that came about and how you could use that or work with that team?
Mark, you probably know more history than I do.
All right. And I mean, we can even have Amy jump on to give that.
Oh, yeah.
CAFs was spun off from RASM in 2015. And as part of that movement or transition, Amy did the initial upgrade of WRF and RASM to version 3.6.1. And then she also created her own domain and region. She's using CLM as the land model as well. And I forget how the ocean sea ice is handled.
Amy's here, fortunately, so she can answer some of these questions as well. And I just saw her hand pop up. So Amy, please go ahead.
I could add to that, Mark, if you like. So basically, CAFs took RASM and turned it into a forecast system. And so basically the domain is just the Arctic Ocean and the surrounding land. All of the components are run at 9 to 10 kilometers. It has all the same components of RASM, except the land model is the NCAR land model, land surface model. And we initialized the sea ice and the SST, and we forced the model with the GFS forecast. And we use the GFS forecast as the initial conditions as well. Yeah, and the cloud properties are initialized. The ocean and the ice are free running.
Cool, thank you.
Thanks, Amy. Thanks for the question, Andy. Are there other questions from the group? I guess one observation I'll make from right at the end there, Hailong, is that you were talking about these black carbon events, right, and transport into the Arctic. And there's a really nice paper that I'm guessing you've seen already, but Lubna Dada from Switzerland put in a paper that looked at the aerosol properties at Mosaic during a warm air intrusion event in the springtime. So it might be interesting thinking about the aerosol transport in general to see how much aligns with what was found in that paper versus not in the model. And granted, that was one specific event, but I bet there are some things that might be translatable to what you're finding with the model.
Yeah, exactly. So although the event-based transport is extremely challenging, but it's also very revealing. Yeah, if the model cannot capture some of those transport, that means some processes must be deficient. Yeah, I will look into that work. Thank you.
Yeah, I'll grab the link and drop it in the chat for everybody. Mike, it looks like you have a question. Please go ahead.
This is a bit more general question, but one of the proposals for trying to limit polar warming has to do with trying to reduce the role of cirrus in the winter and trapping IR radiation. I guess I'm wondering if there are projects going on that are trying to get a sense of how much difference does the cirrus deck make? I mean, how is it being simulated, and does it make a big difference? Because, I mean, if there's going to be proposals about thinning, it would be nice to know what role it's playing right now.
Maybe I'll just try to answer here. So for this project, we're not specifically looking at how the change of perturbation to the system, intentional perturbation to the system, but the cirrus cloud and mixed phase cloud is challenging to simulate in all models. We for aerosol impact on the clouds, we mostly looking at the short wave effect, but I know that in the Arctic, the long wave through ice cloud also very important. I guess that's also part of the focus of this mosaic intercomparison. So we just lost John, but otherwise John can chime in. But those two mosaic intercomparison activities, there's some focus on the model performance in cloud simulations.
Yeah, thank you, Hailong. Other questions? If not, maybe I'll open up the floor for other announcements. Are there any other community announcements that people would like to make or share with this group? Any recent results, upcoming workshops, job opportunities, whatever you'd like. This is a good time to share those things and have them distributed more broadly. All right, I'm not seeing any hands. And so I guess with that, we will move towards closing this meeting. Our next meeting, I believe, is going to be in November. We're working with Wilbert and some of the other communities of practice to have a meeting that's focused on clouds in the atmosphere and models in particular. And Wilbert, I don't know if you want to say anything more about that meeting specifically, but we're working to finalize the date. I know we've been juggling it around a little bit and shifting it, but it will be likely in early November, I believe.
Yeah, thanks, Gijs, for bringing this up. Yeah, so the modelers community of practice is working on a kind of series of seminars or webinars addressing specific biases in the Arctic Earth system in US Earth system models. Back in June, we had a session about Arctic ocean stratification, co-organized by the physical oceanography community of practice. And as Gijs said, for the upcoming session, we'll be focusing on biases in clouds and impacts on surface radiative budgets, and in collaboration with Gijs and Barry from the atmosphere community of practice, but also Hailong representing the PA2. So very excited about that, and we're still trying to settle on a date for that.
Yeah, thank you, Wilbert. And I did just check my email. So at the moment, the front runner for the date is November 7th, just in case people want to put a placeholder on their calendars at 1 p.m. Mountain Time, 3 p.m. Eastern, 11 a.m. Alaska. I think I did all those translations correctly. And so hopefully we will have that date finalized shortly and send out an official announcement through IARPC channels. But we hope to see many of you there. And in the meantime, I hope everyone has an enjoyable October and fall, and we will talk to you again in about a month. So thanks for joining today, and look forward to seeing you all again soon.
Yeah, thank you all.
Thanks for the opportunity.
Thank you.
Thank you.
Bye.